Okay. The recording's working. Great. Okay. So there's two more things I need to talk about in section 6.1 before I can move on to 6.2. So the two other things I need to talk about. The first thing I need to talk about is the idea that you can use the midpoint rule to approximate any integral. Right? You can use the midpoint rule. Like, remember, the midpoint rule is this idea that you can always approximate an integral by drawing rectangles, using midpoints, plugging them in, etc. You can use midpoint rule to approximate any integral, including integrals that represent areas like this. So the idea is I'm going to do an example using this. Again, the midpoint rule to approximate integrals is a useful tool when you aren't able to evaluate them exactly. When you don't have, and there's lots of functions like this that you can't actually integrate exactly. So in a situation where you can't integrate something exactly, the best you can do is approximate it using the midpoint. So, example 6 is a situation which requires a table that's in the textbook on page 428. So the idea is what they've done, actually, I think it's a diagram rather than a table. What they've done is they have taken a swimming pool and they've measured its width at 2-meter intervals. So the swimming pool, it looks like that. And every 2 meters, they've measured the width. So here it's 6.2. Here it's 7.2. Next one, 6.8. Then 5.6. 5.0. 4.8. And 4.8. So they've measured the rules, measure the width every 2 intervals. And they ask you to use the midpoint rule to calculate the area of the pool. Right? So the idea is we can approximate the area. When I'm asking you to use the midpoint rule to do something, I'm asking you to basically approximate it with rectangles or strips. Right? Here the idea is your axis goes from here to here. You're basically trying to integrate from this end of the pool to this end of the pool. So you want to approximate this with strips, you're going to have to cut it into strips. Cut this axis into strips. Now, I didn't actually say what n was. The book didn't say what n was. If it was going to be something like this on the test, I would tell you what n was. Here, n is going to be 4. And actually, if these were evenly spaced, that's where it would be cut, at each of those 4 places. Again, in the book, the diagram is actually evenly spaced. So the first rectangle is going to be here. I'm going to use the midpoint of that first strip. Calculate the first rectangle. The second rectangle is going to be here. I'm going to use the midpoint of that second strip to calculate it. The third rectangle is going to be here. Use the midpoint, because use the midpoint rule. And the fourth one is here. Use the midpoint. Now each of these widths, the width, like this distance has been measured every 2 meters. So this distance here is 4 meters. Right? This is 2 meters here, 2 meters here. This is also 4 meters. This is also 4 meters. This is also 4 meters. So if we want to measure the area of this strip, we're going to have 6.2 times 4. This one is going to be 6.8 times 4. This one is going to be 5.0 times 4. And this one's going to be 4.8 times 4. And if we add that all that up, that gives you an approximation for the area of this pool. So 6.2 times 4 plus 6.8 times 4 plus 5.0 times 4 plus 4.8 times 4. Oh, I made a mistake here. Plus, okay, 6.8 times 4 plus 6.2 times 4 plus 6.8 times 4 plus 5.91.2. So the area of this pool is approximately 91.2 square meters. And so the key thing is this idea of being able to like calculate the area by using, by sort of dividing into rectangles. We can use it also to approximate the area. Divide into rectangles, right? The area of a rectangle is going to be the width times the height, and the height of the rectangle is going to be measured at the midpoint of each rectangle, which is going to be here 6.2, 6.8, 5.9, and 4.8. Any questions about that example? One of the reasons I like asking examples like this is these sorts of examples test your actual understanding of what's actually going on when we're calculating areas, rather than just sort of memorizing the formula to do it. Right here, you sort of need to actually be able to visualize, you know, where are these rectangles going when we're estimating this area. Okay. The other thing I need to talk about is how do we calculate areas using horizontal strips. Now, we use horizontal strips to calculate areas whenever we have, rather than curves being y equals something, we have curves that look like x equals something. So again, we have to use horizontal strips whenever you have curves that can't easily be expressed with an equation giving y as a function of x. So if we have y as something in terms of x, it's easy to, you know, sort of integrate or come up with a curve usually. If we don't have y as a function of x, if you have x as a function of y, we have to do things a little bit differently. So if we have x being a function of y, we'll have curves that look like this. Rather than the curve sort of being a squiggle like this, there'll be a squiggle like this. Again, if you switch x and y, something goes horizontal because something becomes vertical. And if we want to calculate this area, what we can do is we can first figure out, okay, between which two y values do we want to calculate the area? And here, rather than trying to cut this thing into strips like this, we're going to cut them into strips like this. So rather than dividing the interval here into pieces, we're going to divide an interval here into pieces. Right, if we take one of these pieces, we're approximating that graph, that part of the curve with a rectangle. Right, how are we approximating the rectangle? Well, we've got the width of the rectangle here is going to be delta y. Right, and at some point in that rectangle, we have a point yi star. And at that point, we're going to measure that green distance, the distance between those two curves. So the area of one of those rectangles is going to be delta y times, if we want to measure this horizontal distance, we've got to take the x-coordinate of this point minus the x-coordinate of this point. The x-coordinate of this point is going to be f of the sample point. The x-coordinate of this point is going to be g of the sample point. Sorry. So the area of a rectangle is going to be delta y times f of the sample point minus g of the sample point. If we want to take the total area, we can just add all those guys up. Or we can, times delta y. Or we can turn it into an integral. As an integral, it's going to be f of y minus g of y dy. So the idea here is just like we can calculate areas of regions one of two ways. We can calculate using vertical strips, like we just did, or we can calculate using horizontal strips. When we're making horizontal strips, rather than cutting an interval from A to B on the x-axis into pieces, we're cutting an interval from A to B on the y-axis into pieces. In such a situation, rather than having a delta x, we're going to have a delta y. Right? We're going to have these different strips along the y-axis. Rather than having sample points which are x-coordinates, we have sample points which are y-coordinates. And it's the x-coordinates we're going to need to calculate using the formulas for the functions. Right, that's why it's f of y and g of y to give x-coordinates. And if you want to measure the length of this rectangle, we're going to have to take the x-coordinate here minus the x-coordinate here. Which is why we're going to take f of y minus g of y. So the idea is when you sort of switch, rather than integrating this way, we're integrating this way. What happens is basically the x and the y coordinates switch. Rather than f of x minus g of x dx, it's f of y minus g of y dy. So I'm going to do a couple examples using this idea. One thing to mention is if you're trying to come up with what these things look like using your graphing calculator, you need to use what's called the draw-in command under the draw menu. It's called draw inverse. It basically switches the x and y coordinates. One thing you can do if you're good is just being able to like sort of visually switch them in your head. And sadly, the annoying thing is I was trying to get, there's no graphing calculator emulator installed in this computer, so I can't actually show you a graphing calculator screen and show you where that draw inverse thing is, unless I connect to my laptop through a projector, which I don't have the correct cable to do. So, what I'm going to do for today is I'm just going to sort of sketch the graph with y as a function of x and then switch it sideways to show you what would happen if you did the draw-in thing. So if you know how to use draw-in, great. If you're confused about it and you want me to show you, come to my office hours. Otherwise, you can do what I'm doing on the board, which is just sketch it normally and then turn it sideways. So let's suppose you want to find the area between these two curves here. So here the two curves are 4x plus y squared equals 12 and x equals y. Now the key thing here is solving this for y is going to be annoying. If we solve this thing for y, we'd have to take the square root of both sides and end up with this plus or minus in there. Your graphing calculator doesn't like dealing with plus or minus things. So what I'm going to do instead is just solve this thing for x. 4x is 12 minus y squared. So x is 12 minus y squared over 4. Now these two guys, if I want to sketch the graph, firstly x is y is the same thing as y equals x, right? This is the same thing as x equals y. Now if I want to sketch x equals 12 minus y squared over 4, I can start by sketching the graph y equals 12 minus x squared over 4. Y equals 12 minus x squared over 4 is going to look something like this. And then take this thing and turn it sideways. If I turn it sideways, I'll get something that looks like this. This is x equals 12 minus y squared over 4. So rather than something pointing down, we got something pointing left. Anyways, so when you switch x and y, this point here goes to this point down here, etc. I'm just going to make this one, here's the old one, this is the one we're not using, I'm just going to make it really faint, using a dotted line. So really, the region I'm trying to calculate is this green region here. And in order to calculate that, I'm going to need to find those intersection points. Those intersection points happen when those two curves are the same. So to find them, I'm going to set the two curves equal to each other. So 12 minus y squared over 4 equals y. So 12 minus y squared is 4y. 0 equals y squared plus 4y minus 12. So 0 is y plus 6, y minus 2. So y is 2 or negative 6. So this point up here happens at y coordinate 2. This point down here happens at y coordinate negative 6. And if we're integrating this with respect to y, the limits of integration I'm going to need to use are y coordinates, not x coordinates, which is great. I know the y coordinate here. I know the y coordinate up here. So these guys are my y coordinates. I'm integrating with respect to y. When I'm integrating with respect to y, the distance for each rectangle I'm measuring is a horizontal distance. So I'm going to have to take the x-coordinate here minus the x-coordinate here. The x-coordinate here is this guy, 12 minus y squared over 4. The x-coordinate here is just y. And that's the integral I'm going to need to do. For lack of time, I'm not actually going to go through the actual evaluation of this integral. Again, this should be an easy one to do. All you really have to do is simplify this a little bit and then do an extra derivative of each one and plug in the endpoints. I'm just going to leave this, but say this is how you come up with the integral. Yes?
If you integrated that y squared plus 4y minus 12, would that give you the same answer?
Nope, it'll actually be the negative of this. If you simplify this, oh no, it won't give you the same answer, because this is this thing times 4. Right, this is 4 times as big as this guy is.
So would it be easier to just plug that in?
No, because it won't give you the same answer. It'll give you 4 times, it's going to give you 4 times the area of this one. Because we multiply both sides by 4 up here.
Oh, we did?
Yeah. Right, to get from here to here, what do? We multiply both sides by 4. This thing is 4 times as big as this guy is. This guy, if you simplify it, will be negative y squared over 4 minus minus y plus 3. That's what that is going to be. This is similar to this, except it's multiplied by negative a quarter. So again, there is a relationship between this thing and this guy. But the relationship is different each time. And it's just as easy to actually do the algebra here as it is to keep track of what the relationship is each time, if that makes sense.
Can't you just swap the variables as your very first step and proceed as before?
Ah! This is what you'll get. Y is plus or minus square root of 12 minus 4x. And the key thing is we're actually getting 2 different graphs there. This graph here, this graph here is y equals positive square root of 12 minus 4x. This graph here is y equals negative square root of 12 minus 4x.
No, I just mean like actually just
Oh, I see what you're saying.
Yeah.
Actually just...
go 4y. Yeah.
And then just calculate the area of that
The
guy.
area will be
That
the
will
same.
actually work.
Yeah.
So that's one other thing to mention.
Then you don't have to look at it.
Is if you want to, you can actually solve any of these problems by just switching the x and y variables at the beginning, and you should have the same area. Switching x and y will not affect the area. However, it will affect other quantities, such as next section we're going to be talking about volumes. Switching x and y will not affect the area. In some situations, it could affect the volume. There are ways of doing this by just sort of switching x and y to begin with and doing it that way. If you do it that way and you know how to do it to make it work, go for it. I like getting people to sort of visualize it in multiple ways, but yes, if you want to just switch x and y, it will not change the area. And that will, yeah. So Danielle, right? Yeah, Danielle's suggestion does work in this situation. So just changing this to 4y plus x squared is 12, y equals x. Calculating that area, it will give you the same answer. So last example for this section, x equals y to the 4th and y equals square root of 2 minus x. Okay. So here, okay. So let's try to visualize what's going on here. Now here there's 2 actual options here. I could either solve this one for y or solve this one for x. In this problem, I'm going to solve the second one for x, but we could do it the other way around as well. So here we'll get y squared is 2 minus x. So x is 2 minus y squared. And here x is y to the 4th. Now, this is what y equals x to the 4th looks like. This is what y equals 2 minus x squared looks like. if we flip the two of them sideways, here we get x is y to the fourth. Here we get x is 2 minus y squared. And what we've got to find are those 2 points of intersection in order to calculate the area. Those 2 points come with y to the fourth is 2 minus y squared. So y to the fourth plus y squared minus 2 is 0. And then you want to factor this. This will factor as, sorry. Sorry, I'm just going to start it. Y to the fourth is 2 minus y squared. So y to the fourth plus y squared minus 2 is 0. So y squared minus 2, y squared plus 1, no, plus 2 minus 1 equals 0. So either y squared is negative 2 or y squared is 1. This one clearly doesn't work. Y squared can never be a negative number. If y squared is 1, y is plus or minus 1. So this one up here is at plus 1. This one down here is minus 1. And the integral here is going to be the integral from negative 1 to positive 1. Now, which one's to the right? This one's to the right. Yeah, you're taking the bigger x-coordinate minus the smaller x-coordinate in this situation. And there we go. That's what the integral is going to look like. 2 minus y squared minus y to the fourth dy. Any questions about this example here? Yes?
Can we use the symmetry thing since it's from 1 to negative 1? Can we use that?
Yes, exactly. So this thing, if you want to evaluate this integral, this turns out to have even symmetry. You can actually tell because both these things have sort of even symmetry. So this will actually be the same thing as this guy. Oh. So it can be 2 times the integral from 0 to 1 if you want to evaluate this. That will make it a little bit easier to evaluate. Yes?
Would it equal 0 since half is above the x-axis and half is below?
So the key thing here is that we are no longer calculating the area under a curve. We're calculating the area between 2 curves, in which case both these parts count positively. So in chapter 5, when we were calculating the areas, some areas counted positively, some counted negatively. In chapter 6, when we calculate areas, all areas are positive. So that's the key thing to remember is, chapter 5, when we're talking about area, we're still talking about what's called signed area, or net area, which means that area below counts negatively. Here, that's no longer happening. Here, above and below the x-axis, both areas count positive. So any answers to chapter 6 problems should always give you positive numbers. If they give you negative numbers as an answer, it means you made a mistake somewhere. And it could be that you counted this thing negatively rather than positively. It could be how you ended up with a negative answer. So these guys should actually always give you positive answers. So what are they going to say? I'm realizing that this material is definitely taking me longer to get through than I planned. So I'm going to actually, I'm going to take some stuff out of section 6.2 because I'm enough sort of behind the course schedule that I'm going to need to not do all 6.2 in order to stay on schedule for when the test is going to be. So I'm going to, so if you've downloaded the 6.2 slides already, check again later tonight. They'll be different. There'll be some stuff that's been taken out of them. The reason I'll be taking stuff out of them is just to make sure that we can get through all the material in time for the test. So yeah, and 6.2 is like there's enough sort of finicky stuff in there that I don't really want to have to deal with it too much. Okay, any other questions before I move to group problems? Again, I've realized I'm not going to try to start 6.2 today. I'm just going to move to group problems, but it means I'm going to need to actually rethink about what I'm actually covering in 6.2. So here's the group problems for today. This, don't worry about number 3. Number 3 is from 6.2. I haven't covered it yet. We'll do it next class. But try numbers 1 and 2 from these group problems. And before next class, I'll figure out what I'm going to do with section 6.2 in terms of taking some material out.